Hi everyone, and welcome back to Educator.com. I'm Dan Fullerton, and today we're going to finish off the free response section of the 1998 AP Physics B examination. We'll start with problem 5 and we'll work right through to the end. So let's dive right into question number 5. Now number 5 has to do with this apparatus where we've got a tuning fork, a string, a pulley, and a hanging mass. And for part A, it wants us to determine the wavelength of the standing wave. And you could probably just see that by looking at the diagram that that's going to be 0.6 meters. But it's usually a good idea to try and justify your answer on these exams. So I would write something like wavelength is equal to the total length divided by 2, because we have 2 full waves in that region. So that's going to be 1.2 meters divided by 2, or 0.6 meters. And that should be plenty sufficient for that part of the problem. Now for B, it says determine the speed of the transverse wave along the string. Well, we're experts by now using the wave equation, V equals F lambda. Frequency it gives us is 120 hertz, and we just determined the wavelength is 0.6 meters, so that's just going to be 72 meters per second. And for C, it tells us that the speed of the waves increases with increasing tension in the string. So what should we do to the value of that mass, increase it or decrease it, if we want to have double the number of loops in the standing wave pattern? Well, to start that, I'd realize that if we want double the number of loops, we need the wavelength to go way down. And frequency remains the same, so if wavelength is going way down, we need velocity to decrease. So velocity must decrease for wavelength to decrease, which implies then that the mass must decrease in order to reduce the tension. And our key answer here, mass must decrease. All right, and part D. If a point on a string in an antinode moves a total vertical distance of 4 centimeters during a cycle, what's the amplitude of the standing wave? And this is a very tricky question just because of the wording, not usually the concept behind it. But here's what they're saying. If there's our equilibrium point, here's our standing wave at one point in time, that portion of it, and the other portion down here. What they're really saying is as this point, the antinode, travels here and down there, back up to the point where it started, that entire distance it's traveled is 4 centimeters. But the amplitude is just that amount, that displacement. So to solve this, I would say that that 4 centimeters is 4 amplitudes, therefore your amplitude must be 1 centimeter. The tricky part there is reading that question carefully. All right, moving on. Next problem, number 6. We've got a heavy ball at the end of a light string making a pendulum. And we're talking about point P when it's at its lowest point and Q when it's at its highest point in its path as a pendulum. So for part A1, it wants us to draw on the diagram the direction of the acceleration and velocity vectors when it's at point P, when it's at its lowest point. So when it's at its lowest point here in its path, what does that diagram look like? Well, if there's our object, I would say, since it's moving in a circular path, at this point, the acceleration must point toward the center of the circle. And the velocity, assuming it's moving to the right across the screen, well, if that's the case, at that specific instant and point, its velocity vector would probably look like that. Now for A2, we're going to do the same thing for point Q. But at point Q now, we're looking at our pendulum when it's at its highest point over here. That's not overly pretty, but I think you get the idea. Here is our point Q. So now, over here, well, at its highest point there, for a split second, it stops. So velocity is easy. Velocity is 0. And the acceleration, well, the direction it's going to move next is going to be in that direction. If you remember when we talked about pendulums in earlier videos, we even calculated what that acceleration would be, what the force would be that would cause it. So that gets us through part A. Now for part B, it says after several swings, the string breaks. Assuming the mass of the string in there is negligible and the air resistance is negligible, sketch the path of the ball if it breaks at point P or Q. Well, if it breaks at point P, here when it's at its lowest point, what's it going to do from there? It's going to become a projectile. It's going to follow a projectile path, projectile motion or parabolic path. But what happens if the string breaks when it's over here at position Q and it's at its highest point? Well, that'll be B2. If that happens when it's at its highest point, it's completely stopped. The string breaks, it's just going to fall. It becomes a free fall object. So in that case, there's our object. It's going to enjoy a little bit of a trip downwards, free fall. All there is to that one. Excellent. Number 7. Now we're taking a look at an optics problem where we've got a diffraction grating with 600 lines per millimeter, and we're studying the line spectrum of the light produced by a discharge tube with that setup. It tells us the distance of the grating to the screen, and it also says where the observer sees that first order red line at a distance y sub r, which is 428 millimeters or 0.428 meters from the hole. And it wants us to calculate the wavelength of the red line in the spectrum. Well, the first thing I'm going to do is I'm going to figure out the separation between those slits, D. If we have 600 lines per millimeter, then D is going to be, well, we've got 1 millimeter over those 600 lines, which is 0.001 meter over 600, or 1.67 times 10 to the minus 6 is going to be our separation distance. Now, if we've got d sine theta equal to m lambda, oops, I should put my units up here, meters, times m lambda, then our wavelength, lambda, is going to be d sine theta divided by m. But sine theta here, we don't know offhand. But sine theta, that's the opposite over the hypotenuse. The opposite side is y sub r in our hypotenuse, well, right there. And as I look at our hypotenuse, I can get that from the Pythagorean theorem. Our hypotenuse is going to be the square root of, well, it's our length squared plus yr squared. So then I could write that our wavelength is going to be equal to d over m times the sine of theta, which I'm going to write as y sub r over L squared plus y sub r squared square root. Now I can start to substitute in my values and say that lambda is going to be equal to, well, our d we figured out is 1.67 times 10 to the minus 6 meters from right there, divided by m, we want the first order, so m is 1, times y sub r, that's 0.428 meters, divided by the square root of, well, L squared, that's going to be 1 meter squared, plus yr squared, that's 0.428 meters squared. And with a little bit of calculator work, I can show then that the wavelength is 6.57 times 10 to the minus 7 meters, or 657 nanometers. So we've got our first answers there for part A. Moving on to part B, I'm going to switch to another screen here because this will take a little bit of math here. On part B, all right, so 7b talks about the Bohr model and energy levels, and what we're trying to find now is the value for n for the initial level of the transition. So to start, I'm going to figure out what energy this is going to correspond to. So our energy is hf, but we also know that v equals f lambda, which is also equal to c, so I could replace frequency with c over lambda to say that E is hc over lambda. That's going to be Planck's constant, 6.63 times 10 to the minus 34, times c, 3 times 10 to the 8th meters per second, divided by my wavelength of 6.57 times 10 to the minus 7 meters, so that my energy is 3.03 times 10 to the minus 19 joules. And let's convert that to electron volts so we're consistent. So we've got 3.03 times 10 to the minus 19 joules, and we want to convert that to electron volts. We know 1 eV is 1.6 times 10 to the minus 19 joules. My joules will cancel out, and I'm left with about 1.89 electron volts. So now to find the energy of that photon, recall that the energy of a photon is the initial energy minus the final energy, which is going to be negative 13.6 eV over our initial n squared, minus, and our final energy is negative 13.6 over 2 squared, since we're dropping to the n equals 2 level. So we've got to find what Ni squared is equal to, because the energy of our photon is 1.89 eV. So now it becomes an exercise in algebra to solve for Ni. So first I would write we've got Q. Instead of V, I'll put V0. Instead of B, we'll have mu naught I all over 2 pi, and instead of R, we have D. So the magnetic force is Q V naught mu naught I over 2 pi D. And on to part D. An electric field is applied that causes the net force on the particle to be 0 at that point. Well, in that case, if we've got the magnetic force down, the electric field must be providing a force up. So what's the direction of the electric field that could accomplish that? Well, if you want the force up on a positive particle, you must have the magnetic field go up. So up would be our direction, or we could write plus y because it must oppose the magnetic force. And part E. Find the magnitude of the electric field now. Well, remember, the electric field must balance or match the magnetic field in terms of magnitude. So that's going to be, in magnitude, Q V naught mu naught I over 2 pi D. But we don't want the electric force, we want the electric field. The electric field is the electric force divided by the charge. So that's going to be our electric force, Q V naught mu naught I over 2 pi D, and we still have to divide out that Q. Those will make a ratio of 1, and that's going to leave me with my answer of V naught mu naught I over 2 pi D. All right, that concludes our examination of the 1998 AP Physics B test. Hopefully you've got a great start. These are all starting to come together and make sense. Thank you so much for your time, and make it a great day, everyone.